In situ annealing at 650 degrees Celsius, the gold top layer clearly here, the template max phase, 650 degrees Celsius. The clock will start soon, and it's going to be in extra speed. So one frame required every 3 minutes, and the microscopist will sit there readjusting the focus, so you will see some flickering. But it's about the same area that is being imaged all the time. Half an hour, some gold is already on top. The gold is up here on top. Gold is now advancing into and deeper into the max phase, coming in sometimes from the side, also from emerging from the top. So it's kind of using all the channels that it can find. 180 minute, now gold is more or less in the whole material, and with longer time, gold is completely filling the A layer sheets. So this is the end result, and you can compare that to the starting condition where the A layer is silicon, and how the A layer is gold. This was recorded in the Linköping electron microscope, which is a double corrected Titan 300 kilovolt instrument. So this gold silicon reactions, here's a part of the phase diagram. I told you the eutectic temperature. There's very limited solubility of silicon in gold. That is kind of the red line meeting the black axis. But on the other hand, there is much more gold that can dissolve that little silicon that is inside of the template. Actually, you are not supposed to put gold on a silicon wafer for semiconductor purposes. That I think is known. And the reason is the eutectic phase diagram that gold catalyzes oxidation of silicon. So it forms, the contact that you're trying to form becomes a mess if you need it. So the idea is, of course, to use a diffusion barrier, which the semiconducting industry figured out without all this science. That diffusion barrier can be copper, it can be titanium nitride or tantalum nitride, for example. Gold is also known to crystallize amorphous silicon at really low temperature, like 150 degrees Celsius. And as you cool this eutectic system, it's not actually decomposing into the gold and silicon, but it forms metastable phases known as gold silicides, and there's a number of silicides. I have to admit, I have an unfinished PhD thesis. This was supposed to be my PhD work when I worked on it in the late 80s. My supervisor left, so I entered another field of research, which is on nitrides, where I spent most of my time. So at this time, 87 or so, I leave this work. But then many years later, like 2016, we come back to this max phase gold intercalation, and I recollect all my classes in metallurgy and this phase diagram. So now I realize what is happening and why it will not form a good electric contact to silicon carbide. We have now an arsenal of gold intercalated precursor phases or templates. I mentioned this technical 3 silicon carbide too, but it also works to form a double layer gold. You can form that also if you have a titanium to aluminum carbide, where the A layer is now aluminum. You can get gold in. Little gallium carbide, another max phase, also alloy max phases. A max phase nitride can also be used to get gold inside. This seems to be endemic. It's quite common. So I will now spend some more time on this stuff. How do we get the gold out? That quest started for us sometime in 2016, 2017. Quite early, I found the recipe to etch the carbide. Carbides are difficult to etch etching recipes for alloys, steels, so that you can do metalographic work in an optical microscope when you need to etch the surface to see patterns, which are the faces. The material, the substance he used was potassium iron cyanide. It's a nasty stuff if you have it in an acid solution. You never do that. It's blue acid is HCN, and that will be the end of your experiment and yourself. So whatever you do with this, it has to be done in a basic condition. So we add potassium hydroxide. I will show examples now where we start with this gold-capped max face, which is on a silicon carbide template. We do the annealing so that we get gold inside. We do some chemical and mechanical polishing to remove the cap, the remaining cap layer of gold that now has some silicon in it. And we etch off the titanium carbide, and we hope to see 3 gold layers. This table also has some surfactants. I will return to why they can be useful. I'm now going to show what happens if you look at the different concentrations, starting with 100% Murakami reagent. It actually works. It removes the carbide. It works too much. It also dissolves the gold. So that experiment was a failed one. And you probably know that in some not so environmental concerned countries where they mine for gold, they take the scrap piles and they pour a lot of cyanide solution above that to extract the gold, and then they can boil the cyanide and extract the gold grains. We didn't want to do that, so we diluted this solution to 10%. The carbide is still dissolved. However, the gold layers, they cluster, they form packages, and at the end they curl up. How you will remember, metals, gold does not like to stay flat, it likes to form grains. This is exactly what is happening. So we thought we need to dilute even more, so we go to 3%. Now we have triple layer gold. And in the meanwhile, we also realized that, okay, so we are freeing gold layers that are very close to each other. They are like 8 angstroms from each other. So then we figured we can put in surfactants that would hinder gold from contacting with other gold. So that worked in part. And the surfactant that we picked was CETA, which has a long molecule with an end with bromine that has affinity to gold, and the other end will keep other gold layers away. So that worked in part. We have 3-layer gold. One could call this gold in, but we didn't. Now we're at 0.2%. The price we're paying for this is that we need to do the etching for a longer time, and longer time means 2 months. We also realize we have to do this in the dark. The laboratory light has to be down, otherwise the light will catalyze cyanides dissolving the gold. In plan view TM, well, I should just show you this in this square. You can see single layers of gold that are with the titanium carbide. The carbide is gone here, and in magnified part you can see the single goldine layers. Here it appears like there are 2 layers, but it's really that twisted, and the way you project the chromatograph makes it appear as 2 layers. And this is now the discovery of goldine. In plan view, you can see that they are quite small fragments. Here is one, and here is one. The band contrast comes from a rippling, which is natural to many 2D materials. It's also observed for graphene. Now, would graphene be expected to be stable? Well, we decided to run a molecular dynamics simulation. You can see in the plan view that the gold is like in a 1-1-1 orientation for the HKN index. And I'm going to run the movie, and what you will be seeing is some motion of each atom collectively. That is thermal vibration that is expected at this temperature, because the simulations are run at elevated temperature, 700 degrees Celsius. But over this time span of the simulation, the graphene layer remains intact in the different predictions. For comparison, if you take two gold-in layers, two monolayers, and you bring them into some proximity, this proximity is chosen actually to represent the proximity that they have as they emerge free during the etching. I run this simulation, and they attract each other and start forming a bilayer. That is also how the triple layer gets formed. So then we realize that we have to bring something in between here, and that's where the surfactants come into play. I don't yet have a movie of that, we're working on it. Now the properties. One has to realize that when you make a discovery, you submit to nature, they will ask you for properties. So you respond to the editor, you have to be polite. Why properties? You should be concerned with science. Well, we are concerned with readers. We are concerned with citations. So please give us properties or we will reject your stuff. That holds us back half a year, during which time we measure properties, determine at least a sufficient number of properties. We could answer yes, the ability is swift swim and water wave, that works. Lightning rod, possibly we don't know really the color, it should be lightning. The catch rate is not 40%, our catch rate is maybe 1%, the yield is terribly low at this stage of research. The weight is not 15 kilograms, it's less than nanograms, I suppose. Interesting properties. The lattice contracts up to 3%, because there are no atoms on top and on the bottom that keeps atoms in registry, so it takes the opportunity to shrink. With X-ray photoelectron spectroscopy, we also see characteristic extra peaks from the goldine, or the goldine has these extra peaks. That corresponds to an increase by 0.9 electron volts, quite a lot, for the strength by which the electrons are held by the gold atoms. So that gives us not only a characteristic signature of goldine, but also a property that could mean that it bonds stronger, but it could have other catalytic properties. So it could actually be the ultimate catalyst. Gold is already among the best heterocatalysts, however expensive. Now less gold would be needed with goldine, since all the goldine atoms are surface atoms, and it is always a surface atom that is active in catalysis. Possibly, each gold atom in goldine would also be more active because of this change in bonding energy. We envision that one can use this for water splitting to hydrogen, making chemicals from carbon dioxide, possibly flexible transparent electrodes for photonics and optoelectronics. Never underestimate aesthetic value. This could also have artistic coloring effects to glass, although we haven't tested it. I mentioned here transparent electrodes. What color would goldine have? Well, probably no color. It would be transparent. If you make a metal, any metal sufficiently thin, it becomes transparent. It's published that 3-layer gold is 85% transparent. So I would expect goldine to be 95 or 99% transparent. Towards the end, other metalines would be feasible for iridium, platinum, palladium. This is something that we are now exploring, and I will show you an example where we are now, present research with iridium. So this is the case of gold intercalated into the max phase. I should also say that what brought us onto this strait of research is that we wanted to make ohmic contacts to silicon carbide. Silicon carbide is a wide band gap semiconductor. It's used in power electronics. It can get hot, warm. So you need ohmic contacts, which are not easy to get applied to silicon carbide. So we thought that the max phase, which is a conductor, has a good lattice match to silicon carbide. So we started with that, and we wanted to add connectivity for the pads with gold. So the embarrassing truth is that this works well as an ohmic contact until you heat, or if you remove the silicon dioxide that forms here. So silicon dioxide is an insulator. Then we come up in the lab with the idea, well, let's put iridium on top. Iridium is interesting because it's a conductor, but also its oxide is a good conductor. So then we are now faced with a new experiment. We're going to anneal this. And lo and behold, what happens is that as we continue annealing, more gold goes in. I mentioned that we can form bilayers. So now we have the bilayer situation here, and we are going to anneal with iridium on top. Funny thing is that gold goes out and iridium goes back in. So we have a second intercalation, now with another metal. And you can see the contrast clearly here for the coloring of iridium in the cross-section scanning TN image. At this stage of research, we haven't been able to test or verify that we can etch the silicon carbide here without dissolving the iridium. But it's quite possible that we could have a case of iridiumine or IBD, name to be determined in the future. So at the end, goldine has been discovered. It is exfoliated from gold intercalated max phase. I didn't think this was possible, but it became possible when I hired a postdoc who is a materials chemist and knows etching. The conclusion is that goldine exists. It is one atomic layer thick, 111 oriented gold. Surfactants could be useful to hinder goldine from coalescing. You have the up to 3% contraction in lattice spacing compared to bulk, and compared also 0.9 electron volt decrease in the binding energy for the electrons. And Murakami-san was teaching his students, and I'm trying to convey that to my students. Let's try one more time. Always try one more time, don't give up. And never overlook even the smallest change when conducting the experiment. Turn the lights off, turn the lights on. So how we realized was that because of the long waiting time, the 2 weeks or so, some experiments were started in the morning when the lights were on in the lab. And when we were back home later in the evening, we are an environmental conscious, so we turn off, turns the light out. But it was exposed for too long time. But some experiments were started in the evening, and we turned the lights off more or less immediately. And we didn't come back to this shutdown lab for 2 weeks. And then it works. Coming back to nature, I was really upset with the edition of nature. It gave me some satisfaction that the day after the publishing in Nature Synthesis, Nature runs a news feature, and this is the top headline news. And I was very happy. I tell my friends, and they come back 2 days later saying, "Where is it?" And then it was taken out from the top news site in 36 hours, but it was there the few hours of fame. Takehiro Murakami, a late starter, and he gave up actually some more profitable careers to move to another university, starting up. And he ended as director of the Institute for Research in Metallurgy at the Tohoku University of Material Science, which I think is a leading place for metallurgy research. So, if in your undergraduate classes you have looked in metallographic light optical microscope, you need to see such patterns, and that is a steel that is etched with a modified Murakami solution of the sort that we are using. Also, you see the potassium hydroxide, so it's basic. The Damascus steel, it's a lot of folding, but we bring out pattern extra well with the dip of etching in this solution. So I will end here with a summary of the Goldine preparation. You need to have a template. You cap that with gold, you anneal, you have the exchange intercalation, you etch for quite some extensive time in a diluted concentration of Murakami reagent, and you add surfactants, and you can create the Goldine 2D atomic gold sheets. Thank you very much for your attention.